We are indeed honored to have three plenary talks by renowned speakers, both from the academia and industry. We have with us Yang Berbahagia Datuk T.S. Madani Sahari, the CEO of Malaysia Automotive, Robotics and IoT Institute, MARI. We also have Professor Dr. Patrick Massett, the CEO of Technalium Engineering and Consulting, Germany. And we have with us Associate Professor Dr. Norasikin Ahmad Ludin, representing Yang Berbahagia Professor Datuk T.S. Dr. Kamaruzzaman Sufyan, the Director of Solar Energy Research Institute and Professor of Renewable Energy, University Kebangsaan Malaysia. The topics today by the plenary speakers are on the current state of Malaysian automotive industry and outlook for sustainable future, additive manufacturing, a technological and economical mindset change, challenges and opportunities, and an academic perspective and readiness for sustainable future, a case for renewable energy. I would like now to introduce our first plenary speaker, Professor Patrick J. Massett. Professor Patrick obtained his bachelor degree in material science, master and doctorate degrees from the National Polytechnic Institute of Grenoble in France. In addition to his MBA from Paris Dauphine University, he got his habilitation in 2010, the highest French diploma required for a full professorship from the University Paris Pierre and Marie Curie. Prof. Massett started his career in 1998 as research engineer and later became head of research group at Center for Innovation, Competence, Vertucon, Technical University, Berkadami, Freiburg, Germany, before he moved to Fraunhofer UMSICHT as head of department in Sulzburg-Rosenberg, Germany. He has a professorship at the Technical University Koszalin in and is the founder and CEO of Technalium Engineering and Consulting, Germany. Professor Patrick will present his talk today with the title Additive Manufacturing, a Technological and Economical Mindset Change, Challenges and Opportunity. Without further ado, let me invite Prof. Patrick to deliver his talk.
So, ladies and gentlemen, good morning. My name is Prof. Patrick Massett, and I'm the CEO of Technalium Engineering and Consulting. And today I will speak about additive manufacturing, what we can await from this technology, and also a economic point of view. That means this mindset change and dealing with challenges and opportunities. Before starting, I would like to thank the University of Petronas for organizing the conference World Engineering, Science and Technology Congress, ESCON 2020, which is held today due to coronavirus issues. Especially, I would like to thank the people from the ICPER Secretariat and the Department of Mechanical Engineering of the University of Petronas for its kind support on helping with all the issues connected to the online conference that we are dealing with today and since 1 year. And more especially, I would like to thank Professor Dr. Faiz Ahmad from the Department of Mechanical Engineering of the University of Petronas, as we are working together since 2014. And I do think, and I'm convinced that we have a long-standing and fruitful cooperation since I had my professorship at the UTP, and that we have some cooperation and also some publication together. So it's really a great pleasure to be there, and I thank him for supporting me for this plenary lecture today. So before starting, I will give a brief overview about my person and the company Technalium. So I'm Patrick Massett. So I have a PhD degree from the National Polytechnic Institute of Grenoble in France in the field of material science and electrochemistry. Then made at the same time an MBA at the Paris University. And in 2010, then I get my habilitation or my second thesis. So as I mentioned before, I was a visiting professor at the University of Malaysia during my time as a head of department at Fraunhofer here in Germany. And after then, I founded two companies, and now I'm the CEO of Technium Engineering and Consulting. And since last year, I have a professorship at the Technical University of Koszalin in Poland. And my background is material science, coating and engineering technologies, as you can see here on the right-hand side. Well, if I give a few overview about what is doing Technarium, basically there is two main streams, I would say. The one is linked to the education and training, and the other part is the development of product and processes and engineering, but always connected to innovation, as you can see here. Well, as an example of what we are doing at Technarium, we are developing some processes or products. As you can see here, an example about binder-free aluminum heat shield that can be used at very high temperatures, or 1200 degrees Celsius. Here we are developing some alternative processes for powder materials for additive manufacturing. And now if we concentrate on this part here about education and training, we are also offering some online and exclusively online education program like workshop, conferences, summer schools. On here you have one example of the summer school we are supporting this summer on additive manufacturing. And the thing is that we want to promote innovation in different ways. So now I would like to make a statement, and for this I take a sentence from Antoine de Saint-Exupéry. It was a French author and also a pirate. And as you can see here, this sentence from last century in 48, so it's quite old. And it says that regarding the future, it's not a question of predicting it, but of making it possible. And I think this is exactly what we are speaking about today, about technology, innovation, and how we can improve this in a way that it's feasible economically. So let's start from, let's say, something which I think we agree on all on this. This is that there is a global warming of the Earth, and if we are doing nothing, as you can see here on this slide, then we will have an increase of the temperature of approximately 3.5 degrees Celsius in a couple of years. That means that we will have a number of issues to deal with in the future, that some areas they won't be available for people, nearby seas, for example, that we will have also experience some extinction of some species. And also, and sometimes we are forgetting this, that we will also have some economic losses due to global warming. And if we get back to this Paris Agreement, and especially the goals of this agreement in 2015 and then enforced in 2016 at the UN, the target is plus 1.5 degrees Celsius in the future, in reference to the pre-industrial baseline. That means here we have many options that we can activate to reach this objective. One of them is, for example, doing some online conferences, that we are reducing the footprint of traveling also, to develop some new equipment which are less consuming energy, or that we are using lighter equipment, and so on, changing the feedstock, green feedstock, and so on. So today, I'm going to speak about technology, how technology are changing. I'm not going to go in really in details, but just give you a few items that it brings us to think about how we can change our mindset about this. And if you see over the last centuries, we have the Industrial Revolution here on the left-hand side, and then moved to massive production, reduce the cost, to divide the labor with assembly lines, with electric power. And then we move to the next step, last decades of last centuries, with the automatic production, with electronics, with IT, and so on. And now we have, let's say, the third or the fourth industrial revolution, with digital manufacturing, with smart production, with 3D printing, and so on. And this is the future. And today I will just highlight a couple of things about 3D printing and how it's connected also with digital manufacturing, and how it changed also a couple of things on the value chain for the production, and how we can use this as an opportunity, but there are also some challenges. So it's just a few highlights that we can start the discussion later. So just to start, we can compare what is subtractive versus additive manufacturing. If you see on this line here, the classical subtractive manufacturing. So we are starting with materials, and we are drilling, milling, whatever, that we have a 3D check again. Also quite a lot of waste. So that means this waste, they have to be treated, but also it has economic importance, because the question is, can we reuse this here in the chain? And what is the cost? On the other side, if you look now at the line B here down, we're starting from material. And if we are speaking about 3D additive manufacturing, usually it's borders, but it could be also wires. And then we are printing in a way that we have this shape. And then we have to post-process this to remove some remaining borders, to reduce the roughness, and to have finally the surface finishing we are needing or willing. And finally, we have some waste, but much lower compared to the subtractive manufacturing. So, but even with this, we have to think about it. Now, if we are speaking about subtractive manufacturing, the question is, can we do such a complex shape part? The answer is probably no. So this is something, for example, comparable to heat exchangers, new development. Now, if we're speaking about additive manufacturing, I'm a French guy, so I took as an example the French Eiffel Tower. See, it's something like 320 meter high. Can we print this? It's 3D classical printing systems. The answer is probably no. We can do something like this, a few centimeters or tens of centimeters. So you see, if we are just speaking about manufacturing, we see here, obviously, we have some opportunities to do very complex shapes part, but also for large part, there are some challenges, and this is the first highlight I would bring to you. Now, where we are using additive manufacturing. So if you look at this slide, you see the distribution or the repartition about the additive manufacturing by sector. And you see that the most important is for electronics, for vehicles, for medical application, aerospace, and so on. But now we are also starting some new topics or new sectors with architecture, for example, with the use of WAM and so on, for example. We spoke about additive manufacturing since now 2 decades approximately. And you see here, this is the evolution of the number of patents over the years. And it's just like an exponential growth. And we are experiencing since now 10, 20 years. And it shows the huge development around the world, and especially in some countries in Europe, but in the US and so on. Now it's just gaining all the countries. This is also reflected by the scientific publication in academia, research centers, universities. If you look at the numbers of publication, it started a little bit early, 2000 here, but you see that we are experiencing also this exponential shape curve, and it's here until 2014. So we are now in 2021. So it's much, much higher, over 10,000. So that means there is a huge research effort from the companies, private companies, but also from the academia, research institute, and for many sectors that we spoke before. This is connected also with the economic situation, and if you look the market size, you can see that the market size is also following this trend and growing very quickly. I didn't report the numbers after the COVID, so we will have probably like a small break or huge break. But if we look, this is the report from Verda 2019. At that time, it was predicted that for this year we have approximately of 16, 17 billion dollars of the size of the market. So it's quite huge over the world, and this is increasing in this way that we should reach by 2030 something like 50 billion. It's a quite impressive growth. And if we are speaking about this, the growth of this sector, you can see that each year the sector is increasing by 50% approximately. That means within 2 years you have a doubling of the turnover. So it's just amazing. There is very, very less industry that can claim this point. If we look now the partition about the revenues, services versus the product, you see that there is almost the same value, 60% for the services, that means design, conception, and so on, and 40% for the product, that means really the parts, processing, and so on. So you see that it's very interesting if you think about the value chain, because here we can have both on the value chain, either the services from the design of the equipment or automation, design of the part, design of the equipment to print, up to the utilization and all these things. And if you look, it's just like a big the visualization of the companies on the value chain. So you see that we observe there is many companies working on big companies, starting from producing the materials, designing the parts, printing the parts. You see big names like Heroes, Strategies, and so on. Different materials. We are speaking about polymers, ceramic, metals, alloys, even hybrid materials now. And for the production of the materials, you have very, very big names like Oerlikon, GKN, Tekna, Praxair, Aganas, and many others around the world that are providing developing materials for this sector. Up to end users, and here you have also some big names like Airbus or Boeing for aeronautics, for example, but not only. The car producers are using this, or for goods like Puma and so on. And this huge effort from the companies are supported also by national funding and research in the university and the research centers. So here you have also a couple of big names, for example, the Fraunhofer in Germany, you have RMRC, Oak Ridge, and so on, and many others. If we are looking, if I just take the example here in Germany, we have approximately 130 universities working on additive manufacturing. So it means that almost all the universities are involved in this effort in different steps, depending on the focus of the faculties. But it means there is really a huge effort for 3D printing. And that means that the education and training of technicians, engineers is very, very important because it moves very quickly, as we saw before. So if we're back to this additive manufacturing versus subtracting manufacturing, here you have on the right-hand side an example how we manufacture this board that we start from cube and we remove the part at the top. And here we are doing the same, but we are slicing and doing some small parts. So that means we can really create objects or parts with very special design, designed by computers, including some mechanical properties, choice of materials, and so on. You can test it very quickly, print it, and so on, modify it, and so on. Don't forget that we start with 3D printing as prototyping, and now we are moving as a standard production system. So this is the way it works, that it should be cheaper, that we can also print almost everything. One of the key points, I would say, for the industry, this is the cost. It's obvious, but sometimes we forget it, especially in the academia. The thing is, we are speaking about production volume or customization. And if you look at these two graphs, it's interesting that if we look at the production volume, then if you increase the production volume, then the cost will reduce. We estimate that the costs are divided by 2 when you multiply by the volume by 100, something like this. So that means there is somewhere a break-even point. Now, if you are speaking about customization, we saw just before that you can customize the part as you want with additive manufacturing. And this is probably the difference with the classical production systems. And here we also we can define some unit cost on a break-even point compared to these two systems. It's shown here on this graph. So this is something we have to consider when we want to develop a new part, whether we go for classical production systems or we go for additive manufacturing. There's a question of cost depending on the volume and also the complexity of the part. Well, this is one point. But even if additive manufacturing allows some very complex shape, that doesn't mean that we should not also increase the production rate. And now we are developing, or the people are developing different systems, as you can see on this slide, where you can increase the complexity of the shapes, but also you can play with the size and so on. And you can choose the technology depending on the complexity of your part, something like this, or less complex. And also depending on the size of something like this or big like this. And then with this, you have, or you can choose your technology, whether you go for powder bed system or you go for wire deposition system, as I mentioned before. Ideally, it would be that we go there. And you can make a very big part with a very complex shape. So this is probably one of the challenges of the future, to move this curve from here and bring somewhere here. Well, here there is a small resume or summary about the advantages or drawbacks of the technologies. As you can see that with additive manufacturing, you have very low volume, high value parts. On the other side, then cheaper. You have total design freedom, as you can see with this part, for example. So you are reducing drastically the waste. You can even work with exotic materials. You just need to fix the printing parameters. You don't need to change the complete production chain. You will reduce the needs for tooling, because you will have something like a net shape part, and it's just for the post-processing you have to do something. You can increase also the time to market, because you will reduce all the step of the design, the tooling, and so on. And that brings me also to the next point, which is really important, that it's reducing or simplifying the supply chain. Read this in the next slide. So here you have an example about how we can reduce the weight of some parts that can be used in, for example, for aeronautics. Now, if we consider the supply chain model, the classical supply chain model, so you are producing the materials, you are transporting this, printing, and then finally you deliver your printing part to your customer. So that means there is a very short supply chain, and that means here you can really produce a huge number of parts. Now, if you look this and you compare this to the two supply chain, you see this is there are many differences, especially that you can reduce the time. You will also decrease the logistic cost, which is very important. Where we have already seen, you can customize the product. You can have a factory very close to the customers, or even in the building of your customer, because it's you don't need a factory for designing the materials. And finally, also you will reduce the labor cost. It's very important, and you can work remotely. It means you can have the design of your part in one country, the production of the parts in another country, and delivering somewhere else. So that means it's much more flexible, and this also modifies completely the mindset for the supply chain. And this is, I think, one of the key thing of this supply chain. And this will be now increased now in the future with the the digitalization of all the processes. That means you can use the design CAD drawing, send it to the factory, you can print this in different countries and so on, and then you can reduce massively the logistic cost, and this is very important. That means this will also participate to this broadening of this technology in the future. Well, we can also consider the production line or the value chain, for example, for titanium, for the classical way, here for the 3D printing. You see, you have much less steps, that's the first thing. And then also you will reduce seriously the cost and also the weight. Because if you're starting from ores, you should reduce this transport, producing, for example, the sponge, then make compacting with an ingot, then you prepare some billets, transport again, do the machining, and then at the end you have maybe something like 90% waste. Now, if you consider the 3D printing, where you will start from ores, you will use this to get titanium. You will produce some powders, then you will print it, post-print it, and then you have your final part here. The huge difference is that you have less than 5% of waste. If you consider the price of the titanium, for example, this is very, very important. Now I will give you another example where it's really interesting to consider 3D printing. This is, for example, for aeronautics with turbine blades. So here you have a couple of pictures of blades. You see this is very complex shaped part with some holes for cooling. You are doing some coating on the top afterwards and so on. There are many mechanical trends or applied on this, duration, temperatures, and so on. So usually they were casted, and now we are moving to the 3D printing. So you can see that, for example, with EOS, they are providing this. Siemens is working actively on this. They are cooperating. And that makes really sense because we can, if you look at this slide, this was the classical investment casting process, or company Siemens, which is producing this turbine. They were dealing with different companies to provide all this mold materials and cooling, casting, and so on, and then back to Siemens once it has been manufactured, that they can do the turbine. Now, if you look at this demanufacturing process, it's quite different. Even they can modify the design, changing the thickness, for example, modifying the size, the holes, and so on. And then they can print it almost at home, I would say. And then they can modify the surface to get net shape and the quality of the surface needed. So that means here you have really disruption in this case because the company is able to redesign, to optimize the component with very complex geometry, but also they keep control of the value chain. This is very important, and they can with this increase the know-how, and then they will consolidate their process chain to deliver more efficiently and also provide greater internal control about the quality and what they are doing. And with this also they are reducing some or eliminating some steps which are important to reduce cost as well, or to improve the quality. So this is one of the examples where the people change their mindset about the way of making the design of the parts, or changing the design or the repairing and adapting the production line that they can almost do everything by themselves in the factory and not depending on many companies for the materials production and so on. Well, we have seen, and then we come to the end of my production, we have seen that with the 3D printing, we cannot do anything. Took the example of the Eiffel Tower, but there are many, many other examples. And with the classical manufacturing, we cannot do everything. With the 3D printing, we cannot do everything. So most probably there is in the middle a new way or step where we go for hybrid manufacturing. And here there are some pictures describing this, where you can print your part and then you can modify it either by drilling or milling. And here you see one example of the head of this system, where you can combine parts for the 3D and parts from classical CNC manufacturing. And I think this is really the future, that we are combining these technologies. And here this is one step ahead to move forward, that again we are changing our mindset, say, okay, we cannot do everything with one technology, we have to combine. And I know, for example, now in Germany we are developing a network on this, how we can combine or hybrid the manufacturing technologies. It's very important, and they start also at the European level. And this is it makes sense, because if you this is for example the comparison of the production lead times for the manufacturing of closed impellers. If you look at the classical standard casting, you see that you have a value of 14 or 35. With rapid casting, then we decreased to 25, almost 1/3. And if we are combining this, then we are around 2.53. So we are dividing the time by 10. That's considerable. So this is, I think, now the topic we have to think about is how we can combine the technologies, the processes, that we can decrease the production time, increase the quality, increase the complexity for given volume production, and so on. And this will be maybe my conclusion. This can be done only when we also make a very strong commitment. That means that we have also to educate people, train them, technicians, engineers, scientists, and that all these people have a strong knowledge for material science, engineering, and so on, but also that they learn these technologies and that they use the background of material science that can improve the system. So this is a complete, or maybe not complete, but a strong commitment for the future that we have to adapt, or say not the mindset, but our education system, that we include these technologies or this way of thinking in our education program, that we can meet the future requirement for production, that we can also meet the Paris requirement. So with this, I will conclude my talk. Thank you for your attention. I hope that I have highlighted a couple of points dealing with classical and additive manufacturing production, that brings some question and that we have some good discussion. If you want to reach me, here you have my email, either at Technical or at the university for any question. So now I'm ready to answer your question. Thank you very much for your attention.
Thank you very much, Master. for that very enlightening and very comprehensive overview on additive manufacturing. I'm opening now the floor for question and answer. We have one question to start with. This is from Associate Professor Dr. Majdi, University Technology Petronas. Dear Prof. Patrick, could you hear the expansion on application of additive manufacturing in various industries in Germany? Would you be able to share inroads made by additive manufacturing in the oil and gas industry, and how additive manufacturing can meet the high standards of, for example, API? So the question is, how is additive manufacturing in the oil and gas industry, and can it meet the API or any standards?
In oil and gas, you may have some application, for example, for the I was visiting the company Schlumberger for a couple of years in the US, and they were designing some tools for drilling, for example. And it's a very complex shape system, and it's also very expensive. One piece is something like $700,000 US dollar, one piece. And I remember the discussion at that time that, for example, the manufacturer, the suppliers of this part, they had only one or two companies in the US. So it was even very critical from the cost point of view, but also from the supply chain. So here, and the shapes were very, very complex. And I think here the additive manufacturing would be very efficient and useful for this. I know that some companies are also developing some small filters with special alloys for a very high temperatures application. So there are some application for the oil and gas. Basically, always where you have very complex shapes and where the number of units is not so high at the moment. So I'm quite sure that even in the oil and gas, you have some very let's say challenging conditions, either with the temperature or the corrosion issues, things like this. So that's very interesting. The next point is that in this case also this is the post-processing, whether you have some channels and things like this, so all the cleanings of these parts to get all the certification that you are not bringing some residual powders in the system, for example.
I have questions for you. In additive manufacturing, you have shown the graphs of, in terms of the complexity versus volume, etc. I'd like to know, I mean, you have a parts, what is the maximum number of the number in terms of production that is sustainable for additive manufacturing, meaning that beyond that particular number and complexity, then you would go for the traditional manufacturing as opposed to additive manufacturing. Prof, can you? Okay.
This is well, in some cases, the answer is very clear because you don't have any issues with the classical manufacturing system. So that means that the additive manufacturing is the only way to get these complex shapes. So that means here there is no discussion. The next point, I'm not sure there is one answer with a number of parts, because the thing is, the question is whether for the application, what is the added value for additive manufacturing? I would say it's like for a classical application, you will say, okay, you will pay maybe for a part 100. Maybe with another system, you will pay on the 10, but the added value is not the price on the price, but it's on the application. I mean, for example, the mass or the volume, the efficiency of the system, for example. If you look, if you consider, for example, heat exchangers, this is quite a good example, because now you can improve the, let's say, the specific density of heat exchanger, because you are reducing the volume, the mass, you increase the exchange, the specific surface, you are reducing the thickness of the wall to something like 150 to 300 microns, depending on whether it's aluminum or steels and so on. So sometimes the added value is not only the number of parts of the price, but it's really the application. So that is really always in different cases. But even, for example, for the case of heat exchangers, we are speaking about a large number of parts. We are not speaking about a few thousand. It's a really huge amount.
Okay. Another question, Prof, about additive manufacturing. What do you consider as a breakthrough for this technology? Basically, what particular areas will be considered as a major breakthrough for additive manufacturing? Could it be like manufacturing or printing of tissues, or I mean live tissues, or maybe nanoscale manufacturing or something? Prof, please turn on the.
Yeah, evidently at the moment there are some limitation. This is the size of the part. Either big parts, I showed this in the presentation, but also very small parts. So we can imagine that for medical application, for instance, that we are printing, for example, very small part, like I wouldn't call this like nano additive manufacturing. Here we have to change, because even the powder materials, it's a few microns. So if we are speaking about nano, we have to change the way of doing the thing. So that could be really a breakthrough. There are already some work on this to really have some very small parts. I think one of the, because we are speaking about the 3D printing, but we can think about the 4D or 5D printing. That means that we have some systems that are moving with a external effect. So that could be the temperature, it could be a magnetic field, or tension, or whatever. And this, I think, this is also something very promising, because here you can have your 3D part, but also that can be the geometry can be changed depending on the let's say the stimulation you bring, for example. And this, for medical application, could be very interesting for stents, things like this. Regarding the tissue, yeah, I think it could. We can imagine that people we are printing some tissues in the future. There are some now. It's almost on the industrial scale now. This is but still emerging, I would say. But for example, for construction, the small buildings, bridges, things like this as well. So we can imagine that in 5 or 10 years, that we can really build some complexes, not only a small house, but really buildings with additive manufacturing. And I think this is in some region in the world, this is something interesting, because you can build very quickly some residential areas, for example. And the next point, this is for sure, this is not only the process itself, but the materials we can develop in the future with hybrid materials, well, human tissues, maybe this is something different. So there are many options, I would say, on let's see what happens.
Well, thank you, Prof. Patrick, coming to us all the way from Germany. We thank you very much for sharing with us your wisdom and your knowledge as well. We hope you will continue to be with UTP and continue to provide us with your insight and knowledge and sharing of your experiences. So on behalf of the organizing committee and the chairperson of the conference, Associate Professor Dr. Putri, we would like to thank you so much for your participation as our first plenary speakers to this conference. Thank you, Prof. Patrick. I hope you have the best for the day to come.
Thank you very much for this opportunity, and I wish you all the success with your conference. Thank you very much.
Thank you.
See you soon.
Thank you, Prof.
Bye-bye.
Bye-bye. All right, ladies and gentlemen, we now come to our second plenary speaker. I would like to introduce our second plenary speaker, Yang Berbahagia Datuk T.S. Madani Sahari, CEO of Malaysia Automotive Robotic and IoT Institute. Datuk Madani is the CEO of MARI, previously known as Malaysia Automotive Institute. MARI is the focal point, coordinating center and think tank towards enhancing the competitiveness of the automotive industry and overall mobility. Through the adoption of robotics and the Internet of Things under the custodian of the Ministry of International Trade and Industry, Dato' has played an active role in shaping the landscape of the automotive industry through his involvement in the formulation of the National Automotive Policy, and under his leadership, MARI has expanded its scope to cater for the ever-increasing demands for robotic and IoT adoption in Malaysia. Since its establishment in 2010, the Malaysian Automotive Institute now has developed numerous programs and centers of excellence equipped with the facilities to assist the industry, academia, and relevant stakeholders. The existing facilities, programs, and experience within the MARI network will allow immediate access for industry players to develop their capabilities in advanced manufacturing and advanced IT towards Industry 4.0 compliance. Datuk Madani graduated from University of Lorraine, formerly Nancy University in France, with a degree in industrial technology and a master in quality engineering, in addition to being a certified quality engineer. Datuk carries with him 25 years as an executive manager with national and international automotive manufacturers in the area of strategic collaboration, project development, and manufacturing. Without further ado, let me invite Yang Berbahagia Datuk to deliver his second plenary talks with the title Current State of Malaysia Automotive Industry and Outlook for Sustainable Future.
Hello, Assalamualaikum, and a very good day. Firstly, thank you to UTP for inviting me to the event today, and I'd like also to thank the co-organizers to this event. Ladies and gentlemen, I'll be talking about the current state of the automotive industry and the outlook for a sustainable future. Let's talk first about the industry performance. The year 2020 has been a very challenging year, even going into the year 2021. But Alhamdulillah, the automotive industry last year, while there were challenges, the industry thrived. And we can see, number one, from the total industry volume, the industry managed to surpass that 500,000 mark in terms of total sales. Now, other important factors to the automotive industry would be the exports. Now, our parts and components export had been very strong in the last few years, and last year 2020, despite the pandemic, we were still able to export exceeding 10 billion, precisely 12.87 billion worth of exports. Of course, the large part of our export came from the parts and component. Now, in terms of investment, last year, 2020, a total of 5.05 billion, 5.05 billion worth of investment had been implemented in the sector, with an additional jobs of about 66,266. Our benchmark of our auto industry has always been, one of it has been always about the penetration of the energy efficient vehicle. Last year, we have reached a percentage of 88.3% of cars sold in Malaysia having categorized as energy efficient vehicle. Another key important component to the growth of the automotive industry is the value of localization, meaning how much of the supply chain is being localized in Malaysia. And last year, we have recorded a total localization of 9.7 billion. So all in all, it was a challenging year, but it wasn't that disappointed, for the automotive industry, given the figures that I've informed just now. So let's move on now to the current current status in Malaysia with regard to electric vehicle. Now in Malaysia, EVs, the sales of EV make up really very little. It was less than 1% of the total vehicle sales in Malaysia. I think Malaysia, we started to promote EV way back in the year 2009. During that time, the policy has given full exemption to import duties as well as excise duty to hybrids and EVs. While hybrid took off, but not for EV. EV then, EV cars then were still very expensive. And I think one of the key challenging component of EV then was actually the range. Meaning one charge, the car cannot go that far. But now the technology has improved, and we can see that per charge, it is quite normal for any EV car to be able to be driven above or more than 300 kilometers at the minimum, while there are now cars that can go beyond 500 kilometers, even 400 kilometers. There are cars now that can go beyond 400 kilometers, and even some EV models that can go above 500 kilometers. But again, of course, in Malaysia, we still facing, some of the fundamental factors to having EV as really, I would say, as the staple vehicle in Malaysia. One of it is the charging station. We see, some startup companies having now to deploy charging stations, but I think despite that many are saying that we don't have enough charging station, but I really think that charging stations would need to come with the EV, the cars itself coming into the market. Now, as yet, we have yet to really see the local production of EVs, even the importations of EVs into the country. Now, of course, people are saying that it has got to be a policy driven. While that is true, but the fact of the matter is the excise duty on EV now is only at 10%. The bigger factor would be obviously the import duty. So cars that are coming from countries having no bilateral or regional agreement with Malaysia wouldn't have to pay a higher import duty. And that's one of the reasons why the EV cars are still expensive, despite the cost of batteries are now much reduced compared to the cost 5 years ago. Now, of course, there are other things, for example, the protocols of the EV charging and the need to harmonize that to the UN regulation, as Malaysia is part of the WP29. Now, let's just move on to some of the initiatives that has been carried out by MARI. Actually, in the NAP 2020, the vehicle which is we call the next generation vehicles. Now, we mix the notion of EEV and connected mobility. Yeah. Now, energy efficient vehicle as an overall, there is electric vehicle as part of EEV. Yeah. But more importantly is to be recognized as a next gen vehicle. There is this level of autonomous vehicle that needs to be linked with the vehicle. So we are defining next gen vehicle or next generation vehicle as vehicle that is EEV. Okay, it could be EVs, it could be other form of technology, but provided it is green in its product, in its emission and so on, but the other one, it has got to be autonomous. It has got to reach the autonomous level. And in the NAP, we have put forth, a policy whereby Malaysia would need to achieve level 3 of autonomous vehicle by the year 2025. Now, all of that now are driving a lot of regulation or overall regulatory framework and standards to be established. So we are doing that this year, 2021, and by end of this year, beginning 2022, all of the standards and regulatory framework would have been completed to make us prepare, for the achievement of level 3 of autonomous vehicle by the year 2025. Now this is what we call as our connected mobility vision, whereby we actually underscore the big data analytics, whereby we understand that the big chunk of moving forward is the ability to queue data, to really gather data, collect data coming from vehicles that are getting more and more sophisticated, vehicles that are more connected, and definitely it will generate a lot of data, and it requires data for the vehicle to be smarter from year on year. And so that's why the whole idea of big data analytics as the platform to advance further the industry is actually something very important. So under our connected mobility vision, there is the Manufacturing Innovation Center, which encompasses of all these manufacturing, I would say, the policy with regard to lithium batteries or fuel cell, EV interoperability center, and all of that is big data, cloud computing, cyber security, and so on and so forth. Yeah, and of course, the other part of it is the regulatory and the standards that have got to go hand in hand in order for us to move towards the connected mobility vision that will enable the production as well as the rollout of the next generation vehicle, then that will give us really big opportunity to enter mobility as a service, while we understand that all of this will improve further our environmental uptake, as well as it will improve further our overall intelligent transportation system. Now, other things that we need to talk, that I would like to also inform is about the reduction in the electricity intensity that is part of the Green Technology Master Plan. So we are tying in, energy efficient vehicle and next generation vehicle, and also the introduction of EVs. We are tying that into the reduction of the electricity intensity. Yeah, so all of this is actually, in line with Malaysia's commitment to reduce carbon emission up to 45% by the year 2030 as compared to the year 2005. Ladies and gentlemen, at the same time, there is, I've mentioned about EVIC, which is the EV Interoperability Center. So that's something that is being envisioned to be set up in Cyberjaya. So last year we have got the approval for the land and the acquisition. So this year, soon after MCO, we hope after the end of this MCO, we are able, to kickstart the launch, actually groundbreaking for this EVIC Center in Cyberjaya. Yeah, and hopefully it will be fully commercialized by the year between the year 2023 to 2030. But by next year, 2022, we'll be already deploying use cases, in the EVIC Center, and this would be really about descriptive and predictive use cases, the ability to test and commission some models, and also some level of on-site development in order to evaluate and assess I would say the soon to be equipped facilities and machineries in the EVIC Center. Now, early on, ladies and gentlemen, I also talk about standards, so there are various standards that are being drafted at the moment, and some have been completed, but there are a bit more that need to be finalized. And inshallah, by end of the year, all of these standards would be finalized and approved. So we are talking from standards on EEV, standards on EV interoperability center, the AACV, the standards on biodiesel, vehicle roadworthiness, etc., and so on. Yeah. The other part is, I would say, while we are looking, into the deployment of technologies, there is always the aspect of human capital that cannot be left out. So we are enhancing further our training programs, enhancing the current programs which are around the automotive industry certification engineering, around the industry-led professional certificate, as well as the graduate apprenticeship program. We are adding in new programs such as the Industry Forward in the form of SLDN, and we are also now starting also to introduce and execute new programs such as employability and retraining of local talent, as well as reskilling and re-employment of local talent within the ecosystem of the current ecosystem within the automotive sector and other sectors as well that are related to the Industry Forward, that are related to areas whereby it requires digitalization, it requires that interaction between manual and automation. Yeah, it could be also mechanization, need not to be purely robotized, but it could also include mechanization. So new programs are, is really encompassing the nature of the process that can be from semi-manual, to mechanization, up to a full robotization or full automation. So those are the new programs that we are working on today. Actually, we have started all of these programs. Hopefully we could have a good result by end of the year in terms of employment. All of these programs have got target in terms of placement. So not just training for the sake of training, but this is training to ensure that the trainees, the participants, are able to find jobs. They are able to be placed in the industry where their training has more impact to improve the industry. Other programs that new and we are enhancing, there's a lot more of programs also that we are enhancing, some of the basic ones, enhancing the lean production system. Something that has been ongoing for the last 10 years, but this is something that we need to move forward. We need to improve further the manner that we simulate a process. If last time, we simulate a process via video cam, and to see areas of repetition, areas of where there's gap and so on. But now there are software that we can use to perform the complete simulation of a process, and from there we can then determine where are the areas that cycle time could be improved, where there are spaces that could be reduced, and where there are processes also that can be that can be shortened. All of that will improve cycle time, all that will improve the productivity at the process. Another aspect of the new training is the simulation. That's the Marine Simulation and Analytics Center, MASAC. It's a program that we had initiated with some of the vendors and in partnership with Proton. Yeah? So this is a key, I would say, program, and it's also a center in Cyberjaya, whereby we get the vendors to be equipped with the necessary knowledge, hardware and software in terms of doing simulation for their specific process as well as their specific product. We have got new things like smart predictive maintenance data system, something that we are now commencing with Perdua, as well as digital design, digital design smart cooperative platform. Yeah, so that's another area also that we are starting with Perdua and their vendor community. So there's a lot of new program and enhancement of the existing program to make sure that the vendor community or the OEMs themselves are aligning towards Industry Forward, Industry 4.0, are aligning themselves to the importance of digitalization, to the importance of using advanced technologies in improving their process, and therefore will improve their products. Ladies and gentlemen, other areas that we are looking into is also the EV wireless charging system. as well as the battery management system and the electric light commercial vehicle. So these are something that Mari is looking at with our partners, with the vendors, the business community that are already in this space of EVs, in the space of battery production and so on. Yeah, so we actually come in, we enhance further, the technology, we enhance further the supply chain within the EV wireless charging system, as well as within the BMS, as well as the TMS. Yeah. Okay. There are other things that we are also going into now. I'll go very briefly. Now, given COVID-19, Mari, we are also looking into medical engineering. We have introduced our EMUSAFE tracker and EMUSAFE test kit. So these two are hand in hand. It's EMUSAFE tracker is basically an IoT device that could track real time for close contacts. That now we are providing to many factories that now using our Bluetooth. It's based on the Bluetooth 5.0 technology, on the using a clip-on that enable the real-time close contact tracing, of any person being infected by COVID-19 and whom are their close contact to ensure proper quarantine. While the EMUSAFE test kit, this is about the antibody test kit. Mari, we are not a medical related agency, so we partner Sangenix to produce the test kit, but we come in as the big data analytics. We come in to provide the platform to ensure that our cloud services is being used to disseminate the results, as well as be able to perform a data analytics when, based on the spread of data, the spread of antibody results that we are now getting across Malaysia. We are moving also into our hyperscale data center. So this is a bigger picture of our existing, I would say a bigger scale up of our existing data center. So we are envisaging now to invest together with our partners into a bigger hyperscale data center. Hopefully that can be launched also very soon. At the same time, we have already launched and using our cloud services, which is being called the MacWest, the Mari Cloud Web Services. And then recently we have also started to develop Mari Connect, and it is already being live within Mari and Mari stakeholders. Mari Connect is actually, is our own invention, our own design and service to replace Zoom, to replace Teams and so on, because we thought that it is very important for Mari being, the agency that is developing system, that is enabling integration between systems, having this API. It is important for us to have our own Zoom, so we come up with our own Mari Connect. And other things, Mari Intelligence Interview System, we've got that already being executed. We've got Mari Kerja. Mari Kerja is a website, is a web page meant for all Malaysians to enter, and from there they could identify the jobs opportunities and for them to directly apply and to undergo the specific training required prior to their placement. And of course, other things like internship and job placement. So we've got details of it, in the next slide. So I don't have to go through, but these are really the details of some of all the new initiatives that Mari is undertaking at the moment. Okay, ladies and gentlemen, as my last slide, and the way forward to have a bigger impact or to have a sustainable automotive industry, in the NAP 2020, we have listed down all of these incentives, to introduce or to enhance further our EVs. These are the things that are known already, and at the same time, recently government has drafted, an EV accelerated policy, which is more than what being listed down here for NAP 2020. So we are hoping that the new policy on EV will be approved quickly, and then can be implemented or can be announced, to the public and to the stakeholders for, EV to be to come in a stronger manner, in terms of not only production, but even in terms of having EVs as the choice of model, for sharing, for leasing purposes, also to have technology behind EVs to be incentivized if you were to commercialize such technology, having the infrastructure to be also incentivized, not only from the aspect of the infrastructure provider, but as well as the user. For example, how do we incentivize user to upgrade from 1-phase to 3-phase? How do we make sure that power or electricity for EVs, that could be, I would say, given a different rate compared to the normal rate for household and for industry. All of that are now being finalized in the new EV accelerated policy, and hopefully that could be approved and announced and then be executed within this year itself. All right, so ladies and gentlemen, with that, thank you very much for listening. I hope what I've said served some purpose, and serve some additional information to all of you for listening. Thank you very much. I hope that the event, would be very productive and something that could benefit all of us. I surely would benefit in the other lectures that will be undertaken by the other panelists. With that, thank you very much. Assalamualaikum.
Okay. Assalamualaikum, Datuk. Thank you very much for presenting that plenary talks just now. It's very enlightening, very comprehensive on future development of automotive industry in Malaysia. Datuk is not familiar with UTP. I think you have been on the campus several times. Datuk, we have a few questions lined up for you. Let me read the first question here from Dr. Helmi Hussein. Indonesia has set a goal for EV to make up 20% of all domestic cars manufactured, equal to around 400,000 cars by 2025. How about Malaysia? Why are we a bit late in this venture? What factors impede our EV journeys?
You want me to answer that now, or let's have a few questions and I answer quite?
Maybe Datuk can answer that straight, and then we will see other questions.
Sure. Yeah, I've mentioned about the EV accelerated policy. So that is the other policy currently being going to be brought to the cabinet for approval. So that policy is a spin-off from the NAP 2020, but very specific into EV, and we even call it the EV accelerated policy. So in that policy, there is a standard. We have put standards in that policy. I'm just trying to find where I put that standards so that I could tell you exactly. I think, hold on. Yeah, so we put two targets, by the year 2025 and by the year 2030. Yeah, so 2025, that's 4 years from now, and 2030. So by the year 2025, we put a target of actually only 10%. And by the year of 2030, we are expected to achieve between around 20% of total TIB that are going to be made up by EV. But of course, these targets, we are not just talking about cars, but it includes as well motorcycle as well as electric buses, yeah, commercial vehicles. So that is what has been indicated, in the EV accelerated policy. So again, I stress the point that we hope the government could approve this so that we could, make it public, declare it public, and we could get the stakeholders to start their implementation of this policy. But nevertheless, we have already started working out few plans, few projects with parties. I'm sure you have read in the newspaper about SOCA coming into Malaysia, wanting to use EV as the platform for their sharing. So that's something also that we've started discussing about it like a few months ago. So SOCA is confirmed in that aspect, and we are now also talking with several other stakeholders, to bring in EV in the form of sharing, in the form of CKD, in the form of other even components, yeah, batteries, motors, and etc. Yeah. All right.
Okay, Dato', one question. The COVID-19, I think, has impacted all the sectors. And how does this impact our automotive development as well as the target in national automotive policy?
Yeah, it is a challenge actually, and that's a good question. But one thing I can tell you now, the challenge is really to get through this phase one, and phase one of the NCO, so that the factories could open back lah. Yeah. So really the challenge is to bring down the number of cases below 4,000. That's one of the KPI in order to move from phase one to phase two. In terms of the OEMs themselves, they are also struggling. They're struggling not of sales. They've got more sales than what they could produce now. But the problem is they're not able to produce. Yeah, so many OEMs actually, the number of months waiting period has increased now from 3 to probably 4. I'm not surprised if some of the models are now reaching up to 6 months of waiting period.
What?
So once the factory can open and start to operate, there's really a catch-up thing that we need to do. But of course, I think the bigger issue here is next year. So for this year, the number of orders, I think, is unless if there are any last-minute cancellation that I'm not aware of. I mean, these are really very very OEM driven. But as far as I know, as far as the info that I've got from the OEM, they need to play this catch-up game for this year in order to meet the orders that the customers have made. So the issue now here is really next year, because if the pandemic continues and if the economy is affected, the purchasing power for next year will definitely be affected. So we are now planning some form of plan how to facilitate the industry from 2022 onwards. So actually, we are planning to have a few roundtables, to discuss it with the industry players, especially the OEMs and the vendor association, to understand, what are the additional measures that the government can do, and initiative that the industry themselves can also undertake, so that we could facilitate as we move into the year 2022.
Last question, Dato'. What is your advice for researchers? Because we are traditionally doing research in the internal combustion engines and using gasoline and diesel as as fuel.
Look,
what is your advice? Because funding is getting scarce in these particular areas actually.
Really, ICE engine is going to go away. That's my opinion. Even in the NAP, we did put a target by the year 2040. But we're not saying that OEMs cannot sell. No, in the NAP, we say that by the year 2040, ICE will no longer be incentivized. So you can still sell ICE engine if they are customers, but you will not receive incentive. So directly, the prices will be higher, and therefore it will discourage the sales of ICE. Yeah. But other powertrains like EV, fuel cell, hydrogen fuel cell, and etc. These are the newer sectors, the newer powertrains that are being encouraged and being promoted, not only in the NAP 2020. There is one policy that goes until 2030, but also in the EV accelerated policy. So my advice is, please have a look into EV, but specifically into EV, please look into solid state battery, for example, and please look into, for example, graphene based batteries. Please look into level 5 active battery management system. Please look into a high level of thermal management system. Please look into other form of batteries apart from graphene. Maybe in between solid state to graphene, there is some other medium, some other materials that are better off while waiting for graphene to really able to be mass produced. This one. The other one I really would like to insist also is the aspect of connectivity. You know, these EVs, yeah. As we move into the future, cars are getting more intelligent. Intelligence is defined as in connectivity, actually, meaning cars are connected between car, between car and infrastructure, car and environment, really between car and everything. So that aspects of connectivity is something that we should participate. That is really one of the good, I would say, really one of the high prospects in terms of what we should enter in terms of economy, in terms of research, in terms of technology development, and etc. For that reason, the EVIC I've mentioned earlier in my speech, EVIC is actually, probably I did not mention it specifically, but the aspect of connectivity, the aspect of ensuring that the firewall is strong and to make sure the cybersecurity is safeguarded when the car gets autonomous and when the car gets more and more connected. That is one aspect that is important. Now, look, for example, even in cybersecurity, I know in Malaysia there is already one company that has developed its own cybersecurity software. But apart from that, actually, many of our cybersecurity related softwares are all imported. It's all the shelf coming from overseas. So there's also one area that I think researchers should really look into. So apart from IoT, apart from those high advanced sensors that that can enable higher level of connectivity. Again, connectivity between car and infrastructure, and car and environment.
Okay, Dato', thank you very much for that answer. Well, we have come to the end of this session. I'd like to thank you on behalf of the organizing committee and as well as the chairperson of the conference, Dato' Putri. Thank you very much, Dato', for your participation and your presentation. Thank you. So I hope to see you once the MCO is over, Dato'. Thank you.
Yeah, please do. Thank you very much, guys. Thank you for the opportunity. Yeah, thank you.
Thank you, Dato'. Okay. All right. Now we have come to the last plenary talk. I would like to introduce our third speaker, who is representing Professor Dato' T.S. Kamruzaman Sophian, Associate Professor Dr. Norasikin Ahmad Ludin. She holds a PhD in chemistry from University of Wales, United Kingdom in 2012. Currently, she is the Associate Professor, Senior Research Fellow of the Solar Energy Research Institute, Surrey, UKM. She has experience and involved in field of renewable energy for more than 20 years. Her specialization is on advanced materials for solar PV, which includes solar cells and energy materials. Her research interest also is associated with the economic, environment, and policy impacts of renewable energy and energy efficiency projects. She has published and presented more than 100 papers in high-impact journals and conferences. Ladies and gentlemen, without further ado, let us hear from Associate Professor Dr. Norasikin.
A very good day to all distinguished speakers and participants, and I hope everyone is in the good health. I'm Norasikin Ahmaduddin from Solar Energy Research Institute, National University of Malaysia, or UKM. First and foremost, I would like to say thank you to the organizers for inviting me today to give a talk on the role of innovation in renewable energy technology for the low emission pathway. So this is the outline of my presentation today. First, I will touch a little bit background of the technological change and the definition, then the role of the technology innovation in energy transition in order to mitigate the carbon emission. I would like also to highlight the role of renewable energy innovation related to system operation, enabling infrastructure, market regulation, and business model in the current global transformations towards the carbon reduction. Then finally, the way forward of the innovation and transitions based on the timeline targets towards sustainable future. So basically, technological change or technological development is the overall process of invention innovation, adoption, and diffusion of technology or processes. In a sense, technological change cover the invention of technologies, including processes, and their commercialization or release as open source via research and development, especially producing the emerging technologies. The continual improvement of technologies through innovation, in which they often become less expensive. Adoption of technology based on the initial deployment and use of the new technology, and the diffusion of the technologies throughout industry or society, which sometimes involve disruption and convergence. In short, technological change is based on both better and more technology. The diffusion of technology actually is the main factor involved in the key linkages between human activities and the final impact of the global climate change. As you can see in the linkage figure, the human activities and energy demand, of course based on the technology, emit the greenhouse gases, which also increase the concentration of the greenhouse gases. So the changes of concentration will directly increase the average global temperature, and finally will affect the changes in global climate. So role of technology innovation. Now we look on the role of the technology innovation for sustainable energy future. So renewable energy technologies are the main core element of the transition, and their synergies are likewise important. Favorable economics, ubiquitous resources, scalable technology, and significant socio-economic benefit underpin such a transition. So renewable energy can supply 2/3 of the total global energy demand and contribute to the bulk of the greenhouse gases emission reduction that is needed between now and 2050, year 2050, for limiting average global surface temperature increase below 2 degrees Celsius. Enabling policies and regulatory framework will need to be adjusted to mobilize the sixfold acceleration of renewable growth that is needed, with the highest growth estimated for wind and solar PV technologies, which is complemented by a high level of the energy efficiency. So now we look on the how the perspective of innovation in terms of the system operation, enabling infrastructure, market regulation, and business model can bring us forward to the low emission targets. Here the technological innovation, as you can see in the figure, can be divided into 4 categories. Categories that can be adopted for a sustainable future. Innovation in renewable energy system. So still, to ensure the eventual elimination of the carbon dioxide emission will require new technology and innovation, notably for the transport and manufacturing sector, which remain largely ignored in the international debate. More attention is needed for emerging infrastructure issues such as charging infrastructure and other sector coupling implication. So the innovation trends in future power system are looking more on the digitalization, decentralization, flexible system, and also the electrification and end use. As the world shifts to more renewable energy, especially variable ones such as wind and solar, a paradigm shift in the power sector has gradually taken place to meet the transition. In particular, is the growing trend of more focus on the so-called power system flexibility in the academic and industrial sector in this field. So the flexibility of the power system refer to the extent to which a power system can modify electricity production or consumption in response to variability expected or otherwise, or can be described it as the modification of generation injection or consumption pattern in reaction to the external signal, such as price signal or activation, in order to provide a service within the energy system. So flexibility can therefore refer to the capability to change power supply or demand of the system as a whole or a particular unit, example power plant or factory. Flexible generation, stronger transmission and distribution system, increasing storage capacity and demand side management also help to boost system flexibility, as do renewable base heat and production. Increased flexibility should also contribute to long-term decarbonization, which is essential to ensure a sustainable energy future. Another innovation in energy system operation is the natural renewable energy community. As we can describe, it is as a net zero energy community, or ZEC, is one that has greatly reduced energy needs through efficiency gains, such as the balance of energy for vehicles, thermal and electrical energy within the community, which is made by the renewable energy. It is also common, such as zero energy building, or ZEB, system or zero energy, and a classification system for the ZEB based on the renewable energy source used by a building. This is begin with a focus slowly on buildings and expand the concept to define a zero energy community, applying the zero energy building hierarchical renewable classification system to the concept of community. A community that offset of all its energy used from renewable available within the community's built environment. Okay, one of the framework of net neutral renewable energy community innovation is shown in the figure by developing a micropower of renewable energy optimization and system integration using various RE sources such as low speed wind energy and solar to power the regenerative fuel cell. So as you can see in the figure or the photo that I share with you today, so this is one of the net natural renewable energy community project implemented by my institute, Solar Energy Research Institute UKM, which is located at Tasik Chini, Pahang, which using 100% renewable energy from solar. So this distributed energy system is for the rural or orang asli, we call it orang asli community at the area. So another innovation of renewable energy system, as you can see here, is the concept of system operation in low energy building using a PV thermal air, or we call it PVT, for electricity generation, and stack ventilation and PV thermal water for electricity generation and hot water supply. So this is, as you can see, this is the low energy building concept as one of the showcase in UKM using the photovoltaic thermal or the PVT technology that I mentioned to you just now. So another area of the innovation is the enabling infrastructure and technologies. So enabling technologies comprise both the physical infrastructure and the automation technology required to support. For example, greater system integration, data collection and dissemination of system resources. and effective and efficient demand response. So this actually can enhance the function and efficiency of energy system, and thereby facilitate greater deployment and use of renewable energy. So the need for the connected infrastructure of tomorrow. So we make the term of connected infrastructure of tomorrow is approaching faster than you think, which the Internet of Things or the IoT, they are new in critical consideration to think about as one prepared for what is ahead. So to start planning and preparing now for tomorrow network, so we have to understand the requirement for power, light and data today. So we have to be smart about the future. So another innovation is on the smart city. So a smart city is one of the current innovation that using the enabling infrastructure or technologies that can control and manage the city operational and efficiently monitoring the energy consumption of the city. So as we can brief you, the concept of the smart city integrates information and communication technology or ICT and various physical devices connected to the IoT or Internet of Things network to optimize the efficiency of the city operation and services and connect to the citizen. So smart city technology allows city officials to interact actually directly with both community and also the city infrastructure, and to monitor what is happening in the city and how the city is evolving. So ICT is used to enhance the quality, performance and interactivity of the urban services, which is to reduce the cost and resource consumption, especially energy, and to increase the contact between citizen and government. So smart city applications are developed to manage urban flows and allow for real-time responses. So however, there are still challenging in developing the smart city, such as insufficient fund, of course, because it needs high-tech technology, and also lack of the IT professionals, inconsistent network connectivity, and also the cybersecurity risk, because all is using the IoT. So another one is on the achieving economic competitiveness, which is one of the mandatory requirements for a technology to achieve deployment and stable commercialization. So this is based on for the figure that you can see here. So we need higher efficiency, cost competitive and environment friendly solar technology. For example, here is a solar for the technology. So cost reduction is one of the key indicators of successful energy technology innovation. So research on energy technology cost dynamic have concluded that learning in terms of the knowledge generated due to the accumulation of the experience is responsible for cost reduction. So beside that, the policymakers are also interested in policies that will encourage innovation of emerging energy technologies, as well as policies that can improve the production or use of certain established energy technology within the energy system. So we also can see that there is a growing interest in policies that can accelerate energy technology cost reduction. The cost of renewable energy, especially solar photovoltaic, as you can see, has a very tremendous decrease due to the technology and market drive. So the solar photovoltaic energy market has seen huge growth in the recent years, unlikely solar thermal energy, which harness heat from sunlight to generate electricity. Solar photovoltaic or PV is the technology, if we make a comparison between the PV, is PV and the thermal. So PV is a technology that convert sunlight directly into electricity. So the cost of solar PV is steadily competitive. As you can see, the cost reduced from USD $48 per watt peak to USD 0.40 cent per watt peak. So it is also expected that the PV industry is continue to grow and the cost is also continuously reduced compared to the other technology. One of the key drivers actually behind this growth is the reduction in solar module price. So the module is one of the main cost or the major contributor of the highly cost in the solar energy system. So over the next 5 years, solar PV is expected to lead renewable electricity capacity growth, expanding by almost 440 40 gigawatt expected. And then solar module are the main component of the solar photovoltaic system, and the solar module also is composed of solar cell, which is also composed of solar cell, which are small electronic devices. This is the definition of the solar cell actually, which are the small electronic devices that convert sunlight into electricity. A recent study shows that the module cost make up about 30 to 40% of the system cost in Japan and 50% in Germany. So this suggests that the price of the solar module plays a large role in solar PV system deployment. So currently many studies have produced the innovation that can simplify the manufacturing process, which can reduce the cost and more environmental friendly. As an example, the toxic and flammable material, as you can see in the figure, which is one of the process in the conventional silicon solar cell manufacturing, has been eliminated and process become more simple and sustainable. So that is the innovation in the manufacturing process of the silicon solar cell. And also the hazardous and flammable material process stage also already avoided, and the cost to clean the environment is also reduced. So this is all the technology which is a change the current production of the solar cell or the solar module. So the new process of the solar module manufacturing is using the environmental friendly method, which contain non-toxic material, less processing step and lower energy cost. So as you can see, the innovation in the research and manufacturing also affect the deployment of renewable energy. So the advancement of the material use and also the technologies has increased the performance of the electricity generation. As an example, the innovation of the solar cell structure, such as in the form of heterojunction and multi-junction solar cell, has increased the efficiency of the performance up to 45%. So another innovation of the solar module is a photovoltaic thermal collector, which I mentioned in the previous slide, that the showcases of the house that we built in UKM or using the PVT or the photovoltaic thermal. So this is the technology. So typically known as a PVT collectors and also known as a hybrid solar collectors. Photovoltaic thermal solar collectors or PV or T collectors, also or solar cogeneration system, are the power generation technology that converts solar radiation into usable thermal and electrical energy. So PVT collectors combine photovoltaic solar cell, which converts sunlight into electricity, with a solar thermal collector, which transfer the otherwise unused waste heat from the PV module to the heat transfer fluid. So by combining electricity and the heat generation within the same component, this technology can reach a higher overall efficiency than a solar PV or solar thermal alone. So photovoltaic cell typically reach and the electrical efficiency between 15% to 20%. While the largest share of the solar spectrum, which is in between 65% to 70%, is converted into the heat, increasing the temperature of PV module. So PVT collectors, on the contrary, are engineered to transfer heat from the PV cell to a fluid, thereby cooling the cell and thus improving their efficiency. So in this way, This excess heat is made useful and also can be utilized to heat water as a low temperature source for the heat pump, for example. So thus PVT collectors make better use of the overall solar spectrum. So solar thermal, as you can see here, the solar thermal application, which is used for the industrial process heat, space heating, drying, and the cooling. A new pipeline of innovation is hydrogen economy. So hydrogen is a powerful fuel, but numerous technical challenges prevent creation of the large-scale hydrogen economy. So these include the difficulty of developing long-term storage, pipeline, and engine equipment, a relative lack of the Chef engine technology that can currently run safely on hydrogen. Safety concern also one of the another issues currently due to the high reactivity of the hydrogen fuel with environmental oxygen in the air. So the expense of producing it by electrolysis and a lack of efficient photochemical water splitting technology. So hydrogen can be the fuel in a fuel cell which produce electricity with high efficiency in a process, which is the reverse of the electrolysis of water. So the hydrogen economy is nevertheless slowly developing as a small part of the low carbon economy for most of the country in the world. So the comparison with the current infrastructure of coal-fired power plant, it is captured that the electrical energy obtained is only 38% with the 100% of coal. This is when we make a comparison. Yeah? If we use a coal-fired power plant. By the way, by using the modification of the infrastructure for hydrogen production, using the coal, it is indicated that with the 100% coal, we can have 60% of hydrogen for the building, industry and transportation, while 42% can be converted for the electrical energy. So this system gives more benefit to the country, such as cheaper transportation, more energy production, and environmentally cleaner. So hydrogen, we can say that hydrogen is the obvious candidate for the renewable energy carrier for the future due to its availability in form of water, high energy density, and lack of negative environmental impact. However, current state of technology in such that significant advances are needed in the next decade in order to make hydrogen economy viable. So there is still lack of an effective large-scale hydrogen production process from water, while hydrogen storage still falls well behind the requirements set by the gasoline. So when it comes to the power generation, we can say that hydrogen fuel cells are still lagging behind internal combustion engines and conventional batteries in performance and power or weight ratio. On the other hand, significant strides has been made in recent time, which give hope that for the future hydrogen will, or in the foreseeable future, be able to challenge fossil fuel as the primary energy carrier, but only through a sustained and a focused effort. So this is one of the solar hydrogen system developed in UKM. So as we can see here, the Eco House powered by the solar hydrogen system and currently used for the our postgraduate student actually as their workstation. So another one, we are looking on the business model. So blockchain is a technology that enable so-called peer-to-peer transaction. With this type of transaction, every participant in a network can transact directly with every other network participant without involving a third party intermediary. So blockchain technology can change the way we transact with the underlying transaction model, shifting away from a centralized structure towards a decentralized system. So without the third-party intermediaries, this blockchain actually can cut costs and speed up the process. So as a result, the entire system becomes more flexible, as many previously manual work tasks are now carried out automatically throughout smart contracts. So this technology shows a lot of promise. Other than being used to execute energy supply transaction, it could also provide the basis for metering, billing, and clearing processes. So other possible areas of application are the documentation of the ownership, and then the state of the asset, such as asset management, guarantees of origin, emission allowance, and renewable energy certificate. So this technology or the innovation has the potential to radically change energy as we know it by starting with the individual sector first, then ultimately transforming the entire energy market. So however, it is still difficult today to put such model into practice. In addition, there are a number of legal and regulatory requirements that blockchain project must also comply with. So in any case, the actual technology behind blockchain has not yet reached maturity and is therefore still being developed. So one of the market regulation that accelerate the renewable energy innovation and business is the feed-in tariff mechanism. So feed-in tariff is a policy mechanism designed to accelerate investment in renewable energy technology by offering long-term contracts to renewable energy producers. So this FIT or the feed-in tariff has encouraged more participants and also create a demand and market of renewable energy in the country. So introduction of the FIT to Malaysia began as early as 2004, and in 2011, feed-in tariff has proven to be very effective in stimulating rapid and large-scale deployment of renewable energy in many countries such as Germany, Denmark, Spain, and even in our country. So feed-in tariff or FIT remain the most widely adopted renewable power generation policy employed at the national and state or provincial level. Currently, the government has announced that the open application for Malaysia for FIT quotes totaling about 188 megawatt for biogas, mini hydro, and biomass resource in Peninsular Malaysia in June 2021. So the offers of the new FIT code, which has been announced before, would be able to generate 1.5 billion in investment and create 600 job opportunities in the renewable energy industry. So this project approved would begin generating and supply electricity starting from year 2024. So another incentive based on the innovation is the net energy metering. This is another market regulation. So it's also which is also encourage more innovation in renewable energy system. So net energy metering or NEM is a mechanism where an eligible consumer install a solar PV system primarily for his own use, and then the excess energy to be exported to the grid for which credit to be received that may be used to offset part of the electricity bill for energy provided by the distribution licensee or our TNB or SESB to electricity consumer during the applicable billing period. For example, if a residential consumer has a PV system on the rooftop, it may generate more electricity than the home users. So the extra electricity produced will provide a credit against electricity that is in consumed. In Malaysia, for example, the government has started the net energy metering 1.0 in 2016 and NEM or net energy metering 2.0 in 2019. Due to the overwhelming response from the PV industry and in an effort to boost the usage of the solar energy, the NEM 3.0 program was introduced in December 2020 to provide more opportunities to electricity consumer to install solar PV system on their roof or their premises to save off their electricity bill. So the NEM 3.0 will be in effect from 2021 to 2023, and the total quota allocation is up to 500 megawatt. So this is one of the FIT of Interi for rooftop of the one of the residential area in around the university. So this is an example of sharing rooftop for solar PV power generation using the FIT or the net energy metering.